Hello, good morning friends. I Aditya from BSC Chemistry Honors second year is today here to explain the chapter non-aqueous solvents for the visually impaired students. Let's start with the introduction. Most of the chemical reactions are carried out in solutions and the behavior of the substance also depends upon the nature of the solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, easy of purification together with its favorable physical and chemical properties such as long liquid range that is 0 to 100 degree Celsius, high dielectric constant that is 78.5 degree, and specific heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous liquid. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents. The solvents other than water which are used for carrying out the chemical reactions are called non-aqueous solvents. Attempts have been made to find some other substance which could behave as good solvents like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example liquid ammonia, H2SO4 that is the sulfuric acid, hydrofluoride, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly about the important features of non-aqueous solvents such as ammonia and sulfur dioxide, physical properties of solvent and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help you to carry out chemical reactions and separate the products more conveniently. Some of the physical properties of the solvent are discussed below. First one is the melting point and boiling point, that is the liquid range. The melting point and boiling point of a liquid determine the temperature range within which the solvent can exist in the solid under atmospheric pressure. Since most of the reactions in a solvent system are carried out in the liquid phase, the melting point and boiling point give the temperature range within the solvent is useful. The melting point and boiling point for some common solvents are given in the table. From here you can see that hydrogen has the highest melting and boiling point, whereas on moving down the table we see that the water has the 0 degree melting point and 100 degree boiling point. As moving down the table we see that the sulfuric acid having the melting point of 10.4 degrees Celsius and 300 degrees Celsius with the boiling point. It is clear from the table that water has an excellent liquid range from 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperature, while liquid ammonia and sulfur dioxide can act as solvents at only low temperatures. Heat of fusion and heat of vaporization. The values of heat of fusion and heat of vaporization help to know that the nature and strength of forces which hold the molecules of the solvent together in the solid or liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid is called its molar heat of fusion. Similarly, the heat absorbed by the 1 mole of the substance to change from liquid to vapor state is called molar heat of vaporization. Larger the value of heat of fusion, the stronger are the intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitudes of the molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of intermolecular forces, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. The ratio is called Troughton constant, that is denoted by delta H of the vaporization upon the Tb, that is the constant. The value comes out equal to Troughton constant. For normal liquids, if molar heat of vaporization are expressed in calories and boiling point in absolute scale, that is 0 Kelvin, then the Troughton constant has the value of 21.5. If we take delta H of evaporation in joules, a Troughton constant is about 90 in normal liquids. Such liquids exist as independent molecules without any bonds between them. A higher value of Troughton constant indicated the associated molecules. For example, the common solvents like water, ammonia, hydrogen fluoride have Troughton constant value than 21.5 and are therefore associated liquid. The molecules of these liquids are polar. The association of the polar molecules is due to their tendency to orient themselves so that the oppositely charged end of the molecules come near to each other. The molar heat of fusion and vaporizations are given in the table. The inspection of table 2 shows that the values of molar heat of vaporization for the water and ammonia are almost same. This means that the forces which hold molecules together in water and ammonia are of same magnitude. Dielectric constant. The third property is this property is a measure of the polar nature of the solvent and help to estimate the solubility of the polar or non-polar substances in the solvent. According to the Coulombic law, the force of attraction between two charged ions is given by the formula F equal to Q plus Q minus indicates that they are the negative oppositely charged ions upon epsilon naught r square, where Q plus and Q minus are the charges of the cation and anion respectively. R is the distance. Epsilon is a constant called dielectric constant of the liquid. If epsilon is large, the force will be small. As a result, only a small amount of energy will be required to separate the ions, and hence it will easy to dissolve an ionic substance. Thus, in solvents of high dielectric constant, the ionic substance will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compound will decrease. The dielectric constant of common solvents are given in the table. It is clear from the table that, like HF, that is hydrogen fluoride, and H2O are the good solvents for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvents like liquid ammonia and sulfur dioxide are having the small values of dielectric constant show decreased tendency to dissolve ionic compounds, and especially those containing the multi-charged ions. For example, carbonates, sulfates, phosphates are practically insoluble in the liquid ammonia or liquid sulfur dioxide. The fourth property is dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has a large dipole moment and also a large dielectric constant. It is related to the polarity of the bond in a molecule. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvents having high dipole moment have a greater tendency to dissolve the polar or ionic substances. This is because of the fact that greater polarity results in strong bond between the solvent and the solute molecules, and large solvation energy is released. The fifth property is viscosity. It is the measure of fluidity of the solvent. Solvents like water, ethyl alcohol, and carbon tetrachloride having the low value of viscosities and are highly fluid and flow rapidly under the ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weights hydrocarbons having the high viscosities and flow at much lower rates at ordinary conditions. In solvents of the low viscosities, the operations such as precipitation, crystallization, filtration can be carried out without any difficulty. With the increase in viscosity of a liquid, increasing the difficulty of such operations. Now let's discuss something about the type of solvents. Non-aqueous solvents have been classified in many ways. The following are the important classifications on the basis of chemical properties. The first one is protic and non-protic solvents. The solvents which protons, that is H positive ions, can be derived from the solvents are called protic solvents. Therefore, protic solvents contain ionizable hydrogen. Common examples are water, hydrogen fluoride, sulfuric acid, and hydrocyanide. The solvents from which protons cannot be ordinarily derived are called non-protic solvents. These are also called aprotic solvents. In other words, these solvents do not contain ionizable hydrogen atom in their state. Common examples are liquid, sulfur dioxide, dinitro, tetraoxide, benzene, chloroform, and carbon tetrachloride. The second type of the non-aqueous solvents is acidic, basic, or amphiprotic solvents. The classification is based upon the fact that acidic or basic behavior of the solvents. The solvents which have a strong tendency to donate protons are acidic in nature are called acidic solvents or protogenic solvents. For example, sulfuric acid, liquid hydrogen fluoride, acetic acid, etc. Solvents which have the strong tendency to accept the protons are basic in nature, hence called basic or protophilic solvents. For example, liquid ammonia, pyridine, hydrazine, ethylene diamine. Also, the solvents which have neither a strong tendency to gain nor a strong tendency to lose the electrons are called amphiprotic or amphoteric solvents. In the other words, they have neither behave as strong acid nor basic but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol. The third type is ionizing and non-ionizing solvents. The solvents which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. Some examples are water, liquid ammonia, hydrogen chloride, sulfur dioxide, bromine tetrafluoride, and POCl3. These ionize as shown below. In between these equilibriums, I am sure that they can readily converted into forward and backward reaction through the equilibrium. Three solvents are generally polar in ionic nature. On the other hand, the solvents which do not ionize at all are called non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbons. These are non-polar or non-ionic in nature. The fourth type is coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. For example, liquid ammonia, sulfur dioxide, dimethyl sulfoxide, acetonitrile, dimethyl formamide, nitromethane, etc. On the other hand, solvents which are not capable of coordinating with the metal ions are of the solute are called non-coordinating solvents. For example, carbon tetrachloride, saturated hydrocarbons, etc. These are not of much interest to inorganic chemists. Types of reaction in the aqueous solvents. The following types of reaction commonly occurs in non-aqueous solvents. First one is the precipitation or metathetical reactions. The reaction in which the precipitation occurs on mixing two solutions are called precipitation reactions. This type of reaction can be predicted if the values of solubility products of the compounds formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a ppt of silver chloride, leaving barium nitrate in the solution. as shown in the reactions. The second one is salt formation. The reactions between appropriate acidic and basic substance to form salts are called salt formation reactions. In such cases, the solvent used must be of one in which the appropriate acid and basic can exist. For example, sodium uracil cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water, that is the OH negative or hydroxide ion, will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water, and ureide ion can take a proton from water to form the hydroxide ion. However, this salt can be formed in liquid ammonia solution by the reaction of urea with the strong base, the soda amide. The third one reactions is acid-base reactions. The acid-base reactions in non-aqueous solvents can be explained on the basis of solvent system concept. As already learned, according to solvent system concept, an acid is a substance by which direct dissociation or reaction with the solvent gives the cation characteristics of the solvent. Similarly, a base is a substance that gives the anion characteristics of the solvent. The acid-base behavior of the substance depends upon the acid-base nature of the solvent, the character of the solute, and solute-solvent interactions. The fourth one are solvolytic reaction or solvolysis. The reaction in which the solvent molecules react with the solute in such a way that the solvent molecule split up into two parts. One or both will get attached to the solute molecule or ion are called solvolytic reactions. Since these reactions can be occur through the self-ionization of the solvent, the concentration of either cation or the anion gets changed. For example, the reaction solvolytic reaction in the water, ammonia and ethanol are given below. The fifth one is solvation, the reaction in which the molecules of the solvent get attached to the solid species, that is cation, anion or molecule, are called solvation reactions. The species formed in these reactions are solvate. The solvation reactions in water, ammonia, alcohol are called hydration, ammonination, alcoholation, and the resulting solvates are called hydrates, ammoniates, and alcoholates. For example, on reaction of copper sulfate with the ammonia gives ammoniate, having formula CuSO4.4NH3. Now let's discuss some reaction in two common non-aqueous solvents. Liquid ammonia. It is one of the most extensively studied non-aqueous solvent. It is now used as a highly useful solvent and a reaction medium for many type of organic and inorganic synthesis. In most of the physical properties, those of the water are given in the table, showing a great variation or great difference in the properties. For example, taking freezing point having ammonia that is minus 77.7 degrees Celsius and that of water is 0 degrees Celsius. Comparison of the properties of liquid ammonia and water. The comparison of the properties of liquid ammonia and water reveals the following points. Liquid range. First one. The melting point and boiling point of the liquid ammonia are lower than that of water. In liquid ammonia, the liquid range is from the minus 77 to minus 33 degrees Celsius, and therefore it prevents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. Second one is the hydrogen bonding. Like water, liquid ammonia is an associative solvent through hydrogen bonding because it contains a strong electronegative element nitrogen. However, the ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen, and therefore NHN bond is weaker than OHO bond. As a result, the freezing and the boiling point of the ammonia are less. Since ammonia is less associated than the water, it is a better solvent for the organic compounds. The third property is dielectric constant. The dielectric constant of ammonia is minus 30 is 22 at minus 33.5 degrees Celsius as lower as compared to water that is 78.5 at 25 degrees Celsius, suggesting its lesser tendency to dissolve in the ionic compounds. Liquid ammonia is therefore a poor solvent for the ionic substances. Soluble salts include most ammonium salts, nitrates, thiocyanes, and iodides. Fluorides and many of the salts are generally insoluble. However, ammonia has lower viscosity than the water, and this might be expected to promote greater ionic mobilities and thereby compensate to some extent for the effect of the dielectric constant. Fourth one is self-ionization. Both ammonia and water comparable are self-ionization as represented below. Ammonia dissociates into the ammonium ion and amide ion, whereas water is dissociates in the hydronium ion and hydroxyl ion. However, the extent of auto-ionization of liquid ammonia is less than that of water. This is clear from the low specific conductance and lower ionic product. Ammonia is a better solvent than water. The following properties of ammonia can make it better solvent than the water. Liquid ammonia is very poor conductor of electricity. The specific heat of ammonia is more than that of water. Liquid ammonia is less viscous than the water. Liquid ammonia has a high critical temperature and pressure. It has less associated than water due to lesser hydrogen bonding. Liquid ammonia forms strong reducing metal ammonia solutions with alkali metals, therefore it is an excellent solvent for many reduction reactions. Reactions in liquid ammonia. Acid-base reactions. The acid-base reaction in liquid ammonia can be carried out by comparing the reaction in water. Protolysis. Certain compounds like urea, acetamide, sulfamide are which are incapable of donating protons to water can readily donate protons to ammonia in liquid ammonia. These reactions are called protolysis reactions. Hence, these compounds can act as acids in the liquid ammonia. Acid-base neutralization. In aqueous solutions, the process of neutralization of a strong basis and a strong base involve of the combination of hydronium ion from acid and hydroxide ion from the base to form practically unionized water. For example, the neutralization of a hydrochloric acid and sodium hydroxide can be explained as it is similar way the neutralization of an acid as a base in the liquid ammonia involves the combination of the NH4 positive ion from acid and NH2 minus ion from the base. There are many examples of the amphoteric behavior in the liquid ammonia. The compounds that dissolve both in acids and base are called amphoteric substances. For example, in liquid ammonia and zinc amide shows amphoteric behavior analogous to that of zinc hydroxide in the aqueous solution. Reactions of amino acids. Amino acid is a substance that furnishes NH4 plus ion in the liquid ammonia. Ammonium halides, nitrates, thiocyanes are very soluble in the liquid ammonia, giving NH4 positive ions, and their concentrated solutions can act as amino acids. We know that the acids give the hydrogen with metals in aqueous solutions. In a similar way, the amino acid solutions of ammonium salts in the liquid ammonia reacts with alkali and other metals to give hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolves many metal oxides to their behavior. Reaction of amino bases. Amino base is a substance in which liquid ammonia solution gives NH2 negative ion. The commonest base is potassium amide, which is more soluble than lithium and sodium amides. Metal salts react as amino bases to give the amides, imides, and nitrites, which get precipitated in the liquid ammonia. The second reactions carried out in the liquid ammonia are the precipitation reactions, which involve the double decomposition because of the differences in the solubilities of various substances in water and in liquid ammonia, and larger number of precipitation reactions which are not normally possible in water, have been reported to occur in liquid ammonia. The third type of reactions are ammonolysis. The sololytic reactions in liquid ammonia are called ammonolysis or ammonolytic reactions. These are analogous to the hydrolysis reactions and involve the attachment of ammonium ion to or amide to the reactant. For example, hydrolysis of silicon tetrachloride occurs as forming the silylic acid having the formula SiOH whole 4. The fourth type of reactions are complex formation reactions. Many complex formation reactions in liquid ammonia are reported which are similar to the reactions occurring in the aqueous systems. For example, zinc nitrates reacts with potassium amide to form insoluble zinc amide which dissolve in excess of amount due to the formation of complex compound of the zinc having formula K2ZnNH2O4 that is soluble. The fifth type of reactions are formation of ammoniates. Just as water forms hydrates, ammonia also forms ammoniates with many inorganic salts. In these compounds, the ammonia molecule are coordinated to the cations, such typical ammoniates are BF3 plus ammonia in the presence of liquid ammonia gives BF3.NH3. Similarly, many compounds also react like that. The sixth type of reactions are redox reactions. Liquid ammonia can act as an excellent medium for the redox reactions. In liquid ammonia, the oxidizing action of the strong oxidizing agents is weaker than in the water solution. For example, nitric acid in liquid ammonia does not act as an oxidizing agent. Similarly, KMnO4 in liquid ammonia can act as a very weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, alkali metals can act as very powerful reducing agents in liquid ammonia. For example, sodium metal in liquid ammonia reduces to copper, KMnO4 to K2MnO4, etc. The solutions in liquid ammonia. The electric constant of the liquid ammonia is low, therefore is expected to be a poor solvent for the ionic substances. Amongst the inorganic compounds, all ammonium salts, nitrates, thiocyanates, and iodides are soluble in the liquid ammonia. Oxides, hydroxides, carbonates, phosphates, sulfates, and most of the sulfides are insoluble. Most chlorides are insoluble in liquid ammonia, and the solubility among the halides increases as most of the iodide, then of bromide, then of chloride, and lowest of the fluoride. Solution of the alkali metals in liquid ammonia. The most striking property of the liquid ammonia is its ability to dissolve the alkali metals. The resulting solutions are blue and extremely good electrical conductors. The important characteristics are as follows. These are blue in color and the color is independent of the metal dissolved. When the concentration of the metal is increased, the color changes to the bronze and show metallic appearance. If the reagents are pure and dry, sodium solutions in liquid ammonia are stable and can preserved for the several days. The ammoniated ions electrons are responsible for the blue color of the solution. This is due to the absorption of visible light by ammoniated solutions. The electrical conductance is also due to the ammoniated cations and electrons. The conductivity for metal in liquid ammonia is comparable to that of an aqueous solution of a typical ionic compound. As the concentration of the solution is increased, the ammoniated cations and electrons associated resulting in the decrease of conductivity. Advantages of liquid ammonia as a solvent. The dissolution of the alkali metals without chemical reactions is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metals can be recovered from the solution by evaporation. The second advantage is the alkali metal solutions are the strong reducing agents, even stronger than the hydrogens. Ammonium salts dissolved in the liquid ammonia can act as amino acids. These find application in a preparative chemistry. Disadvantages of liquid ammonia as a solvent. Liquid ammonia has an offensive odor, therefore it requires special technique to use it as a solvent and reaction medium. Liquid ammonia is hygroscopic in nature, hence all the reactions are carried out in the sealed tubes. The liquid range for the liquid ammonia is minus 33.3 degrees Celsius to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working in the liquid ammonia. Now let's study the second known aqueous solvents, that is liquid sulfur dioxide. The liquid sulfur dioxide is a non-protic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of the most known aqueous solvents used in the industry. Under normal conditions of temperature and pressure, sulfur dioxide is a gas but can be readily liquefied and maintained in the liquid phase. It has a liquid range of minus 10 to 75.5 degrees Celsius and can be used as a solvent. It can be easily purified by passing the gas through the sulfuric acid and through the P2O5, that is pentaoxide diphosphorus, to remove traces of water. If its dielectric constant is small, that is 15.6 at the 0 degrees Celsius, and therefore it's a good solvent for the covalent compounds. The characteristics of the physical properties are given in the table. The structure of a sulfur dioxide molecule. It is just have a angular structure as shown, having the bond angle of 119.5 degrees Celsius and the bond length, that is 1.43 angstrom. Solubilities of the compounds in liquid sulfur dioxide. Among the inorganic compound, iodides and thioethanates are most stable. In case of alkali metal halides, the solubilities are in the water, having the Mi, that is iodides, are more stable than bromides, that of chloride and fluoride. The uri-negative polyatomic anions such as ClO4, NO3 negative and BF4 are generally more soluble in liquid sulfur dioxides. Salts of multi-negative anions such as sulfates, sulfides, oxides are practically insoluble. Most of the ammonium, thallium and mercuric salts are soluble. It is an excellent solvent for the covalent compounds. Many covalent substances like halogens, interhalogens, phosphorus halides, oxyhalides of sulfur, phosphorus, etc. and halides are soluble in it. Metals are insoluble in liquid ammonia. Reactions in the liquid sulfur dioxide. Acid-base reactions. Liquid sulfur dioxide undergoes the autoionization as of SO2 positive and SO3 2 negative ions according to the solvent system concept of acids and bases. The compounds which give thionyl ions in solution would be act as acid, and whereas compounds giving sulfides ion liquid in the liquid SO2 gives are treated to be bases. For example, the thionic chloride in liquid ammonia gives the thionyl ions which can react as acid, and on the other hand it reacts as base. The second type of reactions are solvolytic reactions. In sulfur liquid dioxide are not as common as they are in other prototic solvents such as liquid ammonia. Some reactions are given below. Ammonium acetate is solvolized as given below. Ammonia it is having the formula given as seen in the diagram. Certain covalent halides such as PCl5, PBr5, UCl6, ASCl5 undergo solvolysis in liquid SO2 in the sealed tubes. Many binary halides such as antimony trichloride, antimony pentachloride, silicate tetrachloride, tin tetrachloride, vanadium trichloride, SCl3, SCl4, moscium hexachloride do not undergo solvolysis in liquid dioxide. The formation of the solvents, that is addition of compounds with solvent, is known. Typical examples of the solvents are NaI.4SO2, RBI.4S2, etc. etc. The third type of reactions carried out in the liquid Sulfur dioxides are precipitation reactions. A large number of precipitation reactions are carried out in the liquid ammonia due to the selective solubilities of the compounds. The precipitation of the several insoluble compounds in liquid sulfur dioxide can be carried out by treating them with the soluble compounds in sulfur dioxide. Such of the reactions are showing below. The fourth type of reactions are complex formation reactions. A large number of complex ion formations in liquid sulfur dioxide have been reported. For example, the solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium iodide. This is due to the formation of the complex that is Ki3 or Rbi3. Similarly, the increase in the solubility of the cadmium iodide and mercuric iodide in the liquid sulfur dioxide is attributed to the formation of the complexes. Fifth type of reactions carried out in the liquid sulfur dioxides are organic reactions because organic compounds are soluble in it and have a relatively inert solvent. Some common examples are sulfonation of the aromatic hydrocarbons by sulfur trioxide and chlorosulfuric acid. Liquid sulfur dioxide has also been used as a solvent for the Friedel-Crafts type reactions. In these reactions, AlCl3 is used as a catalyst which is highly soluble in the liquid sulfur dioxide. The sixth type of reaction carried out in the liquid ammonia are crystallization of the sulfur dioxide. These reactions are also known as solvation reactions like water and ammonia. Salts having sulfur dioxides of water crystallization also have been observed. Some common examples are sodium iodide, .4s2o, potassium iodide, .4s2o, etc. etc. These are formed with the highly soluble salts which are analogous to hydrates. The seventh and the last type of reactions in the liquid sulfur dioxides are the redox reactions, which behave as oxidizing and reducing agents. Liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply acts as a medium for the certain redox reaction. For example, iodine is liberated from the potassium iodide in the presence of antimony pentachloride in liquid sulfur dioxide. Some special features of liquid sulfur dioxide as a solvent. It is an inert solvent having low melting point and therefore allow reaction to be carried out at low temperature. It has low boiling point. This allows easy evaporation and therefore removal from the reaction mixture. It is unusual solvating powers for covalent and electrovalent compound. It is better medium that for the covalent compounds like hydrocarbon and used for the purification of the some petroleum products. It can be used as diluent and superacid medium which help in reducing its viscosity without affecting its acidity. Thank you. Now this chapter is completed.